Hello everyone and welcome to this introduction video of generic IK, the version 1.1. The main highlights of version 1.1 is that now we have motion freedom, also known as motion limits, to constrain the rotation of each joint in a chain. Plus, we now have 3 inverse kinematic solvers and 1 forward kinematic solver, and I'll go through them one by one in this video. Alright, I've loaded a new scene. It has nothing special loaded in it except this player, and nothing attached to the player except the animator component, rigid body, and all that plain stuff. I have here 2 spheres, which I'm gonna use for this demo. Now in this demo, I'm gonna demonstrate the basic inverse kinematics script, which is the out-of-the-box solution for kinematic simulation. Basically, it gets you up and running really quick with inverse kinematics. Anyway, so how it works, you basically get your character in the scene, you drag and drop the script on it, inverse kinematic script, which is located in the core. Now, the first thing you want to do is initialize the rig when it is a humanoid rig. If it's a generic rig, you will get a different UI, but that's a story for another time. Just click on the initialize rig, and it automatically builds the chains for the right arm, the left arm, and so forth. In addition, you get 2 new arrays. One is called other chains, which an array that you can resize to create as many chains as you want. There's now a new chain called dynamic chain, which I'm gonna go through later. It's basically the forward kinematics solver that's newly included in the package. Now the UI is pretty simple. First, we get the option to choose what solver do you want to use. It used to be 3 in the last version, analytical, CCD, and fabric, but now the algorithms have been reworked from the ground up, and I decided to give up on the analytical for other things. Now we have 2 main reaching solvers, and by reaching I mean the solver. The goal of the solver is basically to reach an object in 3D space. Now we have cyclic descent and fast reach. The difference between cyclic descent and fast reach is pretty simple. Cyclic descent basically applies or utilizes the motion constraints while solving. Fast reach does not. Fast reach was more designed towards reaching a target as fast as possible, as efficient as possible, disregarding any motion constraints that that chain might want. If you want to use motion constraints, just use the cyclic descent or the fast reach. Alright, both solvers, by the way, work with animated and unanimated rigs, so it doesn't matter which rig you apply this upon, it's gonna solve as that's fine. Now let's get started after I initialize the rig. Now I'm gonna go to the right arm chain. I'm gonna expand this and assign the sphere as a target. I'm gonna put the weight as 1 and I'm gonna give it 10 iterations. Basically, the more iterations, the more accurate the cyclic descent will be, because it will run 10 times per frame. Anyway, so yeah, I've got everything here working. Now let's give it a run. Yep, by the way, this sphere has a simple script that moves it up and down, just for this demo. And yeah, that's pretty much all you need to set up a working IK solution. Now let's try this with the fast reach. Also same thing, but as you can see, the fast reach is more accurate. It does not need 10 iterations to achieve its target. You can get away with 2 maybe, or even 1 iteration. But it does not apply motion constraints at all. Speaking of motion constraints, let's try and apply the cyclic descent on this leg, the right leg. I'm gonna set this as the target and slowly increase the weight. And as you can see, Now, to the solver, this result makes sense. It's basically how the solver is supposed to work, um, solving the IK chain no matter what orientation it spits out. And for that, we use a special kind of algorithm that applies motion constraints after the solver does its job. And you can find this motion constraints options in under the joints tab. So if I go here, I have three joints, this one, and I know this joint is the one to be fixed. So I'm gonna go to this joint, and I get now an enum called motion freedom. It has three options. Full means it's gonna spit out the rotation that the solver gives. It's not gonna change anything. It's gonna give full freedom to the joint to do whatever it wants. Now, we have two other options, full restricted and a single degree. Full restricted means we're gonna basically choose an axis. It's gonna twist itself around these axes and swing along the other two axes. I'm gonna put this in action in just a moment. Um, and the single degree is basically gonna take an axis and it's gonna rotate along these axes and nothing more. It's not gonna give a swing along two axes. It's gonna only give a swing along one axis or 1 degree of freedom. Okay, let's test the single degree. Now I know by experimenting that this joint must give a minimum rotation of minus 130 degrees and minus 20, which are arbitrary numbers that I got just from experimenting and trying out. And right now, as you can see, the leg is now constrained. If I move the sphere, let's go to the side view. If I move the sphere, it does not give weird results anymore. Now, if I come right here and I say, let's say, from minus 130 to let's say 40 degrees, now you see how the leg is now being deformed or applying the rotation limits basically. All right, now let's talk about the other motion freedom option, which is the full restricted. As I said, the full restricted is gonna take an axis and it's gonna swing along two axes and twist along these axes that we chose. For example, in this joint, the twisting axis is actually the y-axis and it's gonna swing along the x and the z-axis. So I'm gonna come here and say the axis is 1 on the y, and I'm gonna put this to 0. And just for demonstrating purposes, I'm gonna put the max angle to 30 and the twist to 0, just to show the effect that it will have. And I'm gonna disable the animator, and yeah, I'm gonna put the weight of the parent bone to 0, just it doesn't move. And all this is just for demo purposes. Now let's test. And as you can see here, the leg does not go any further away than 30 degrees. And if I increase the max angle, it slowly increases to get to the target. And as I said, it swings along the x and the z axis. So if I move the sphere in this direction or this direction, it's gonna basically rotate only 30 degrees. Yep. And yeah, that's how the full restricted motion freedom is supposed to work. And the twist is also the same. If I give it 0 twist, that means it's not gonna twist at all. And 180 degrees means it has full twisting motion range. Okay, alright, and now let's talk about the third inverse kinematics solver, which is called directional swing. Now, directional swing, basically what it does when you build a chain, you have to choose a look at axis, which the solver is going to use to look at a target. And how it achieves this is basically by rotating the hierarchy of joints so that this look at axis of the end effector points at the target. Now, how this could be useful? Now, it could be useful for a number of things. For example, in this demo right here, look at demo, you can use this behavior to achieve a look at behavior. You can use this for a swing, for example. If the character wants to punch the face of an enemy, now the joints in the spine and the torso are gonna orient themselves so that the fist actually hits the face instead of the animation being offsetted by some degree. Now let's test this. This is a very simple script. It has nothing to it except a chain, joints which I have previously built, just the spine joints, and I look at axis which I set to 1 because the head actually, because if I go to the head I see this axis is the Z1. I want it to point at this sphere. Now, and the sphere itself has nothing attached to it except a script that moves it in a circle. Okay, now let's test. Let's run and test. Now, as you can see, the joints are rotating themselves so that this head, this head, yeah, this axis is always pointing at the target. And I can play around with the weighting, so I can, for example, give the most lowest spine less influence over the whole chain and so forth. And I can do that by coming here and dialing these values, the weighting values. Let's take a look at another use case, which is the swing case. Now here in this simple position, I have a player which has a cube, and that cube should be swung at this sphere right here. And for that, I have this simple script. Also the same thing, I will have a chain. I have a look at axis, and now I've introduced 2 more parameters. Now the chain itself only goes till the second spine, this one. But still I want the arm itself to be hitting this target. So there is an offset. There's this little offset. And a way to compensate this offset is by using a virtual end effector. Now, what a virtual end effector is basically a transform object, an arbitrary object that I use to offset the end effector a certain amount so that I can achieve the goal that I want. So for example, I don't want to include so what I mean with that, I don't want to include the arm, the chain. So I've basically created an empty object which is located at the shoulder of the player, that I use to offset the player. So it's not included in the chain. It's just there to offset the chain a little. Now I've got another option, offset in animation, because every animation is different. I've been experimenting with it and I got these values. It's just a simple offset that offsets the animation itself and the real life or the real world goal object. Now let's set this to motion and see what happens. As you can see, now the animation looks a little bit weird, but it's just an animation thing, so it doesn't matter, just a demo. This sphere, if I move this sphere up and down, it's always gonna be pointing at it. Yeah. And that's basically the swing at demo. Now this swing at demo and the previous one, the look at, use the same solver, which is the directional swing solver. but they are utilized in a different way, basically to achieve different effects. So in core, there's nothing new added to these scripts. It's just a demo script that uses the same solver to achieve different results. Yeah, and that's pretty much the end of this look at demo, and I'm gonna go through the fourth and the last solver in the package. I'll be back. Alright, I'm back. Now, in this simple demo, I have this set of capsules that I've put together in a chain. I've put the inverse kinematic script on them and a script that moves them up and down. Now, the inverse kinematic script, when put in a generic rig, it gives you two options. An array of chains so that you can use the 3 or the other two IK solvers with them, and a second array that says dynamic chains. Now, dynamic chains uses the fourth and the newest solver in the set is called chain kinematics solver. Now, what that is, it's basically a forward kinematic solver that simulates physics on a chain. Now, I have one element here, which is the chain itself. The UI is also pretty simple. You get the chain, it has a weight and the joints. And with the joints, you also get the motion freedom and all that stuff. Now, you get a solver fall off, which is basically a graph that represents how the weighting or the influence of the overall solver would be over the length of the chain. So this graph in this particular case is linear one. That means the the very first joint in the chain is this one. It's gonna have the solver is gonna have 0 influence over it, and the very last joint in the chain is gonna the solver is gonna have 100% influence over it. And you can dial this up however you want. You can use different functions. You can even make it linear, make it constant, whatever to your liking or whatever to your needs. Now we get a gravity field which simulates gravity over the length of a joint, moment of inertia, stiffness, and torsion damping. Now, moment of inertia basically is how hard does an object resist its change in rotation. It's basically like mass but for rotation. Now, stiffness is pretty straightforward. It's stiffness, how stiff the object is, the chain, I mean. Now, torsion damping is basically dampening of the torsion. Now, torsion means how fast does an object recovers from its deformation. Okay, let's put this to action and see what happens. I'm just gonna turn down this script. I mean, turn off this. Turn off the script. Yeah, and as you can see, as I move the chain, I rotate it. Everything gets affected by the movement of it, and there is physics applied to it. So if I set gravity to 0, now it has no gravity affected to it at all. Now I can make this faster by cancelling the damping, so it's 0 now. So if I move, it keeps moving because there is nothing dampening the movement of it, which looks a little bit silly, but yeah. And that's pretty much, this is the fourth solver of the chain. It's the newest one. So yeah, that's pretty much it. And I hope you find this video useful, and see you in future versions of generic IK.